So, welcome student to the new class of Introduction to Nonlinear Optics and its application. So, in the last class we discussed about the four-way mixing. So, today we will going to give you one correction, because in the last calculation it depends on what value you are taking regarding the electric field. So, before starting the class, let me once again remind you that according to our notation, the electric field E for a particular wavelength omega I was represented by half of say E1 e to the power I k1 z minus omega 1 t, if the frequency is omega 1 plus complex conjugate of that. Now, in many books the complex conjugate term is not there, and if I want to take this complex conjugate term, then one half term we need to add with that. So, according to our convention, this half term should always be there. So, with this electric field, if I try to find out the implication of four-way mixing or the role of four-way mixing in some frequency generation, then in the last class we figure out the expressions of individual field E1, E2, E3 and E4 and how they are coupled to each other under four-way mixing. So, during this calculation, since this half term was there, we need to take this half term into consideration, and it should be 3 by 4, but in the previous slides or in the previous class slide, it was written 3 by 8. This fourth term will come because in the both side we have a half term. So, this half term will cancel out and you will get a fourth term here. So, these small corrections I just wanted to make before starting the class, and also for four-way mixing in this degenerate process, if I want to find out the frequency omega 4, which one can generate through omega 1 and omega 3, then what happened that I can excite, I can generate the electric field E4. So, E4 electric field can be governed by some differential equation, and we also calculated the differential equation, and this differential equation there was a 3 by 16 term. Again this half term we need to consider, and it because of this half term it should be 3 by 16. So, you should be careful enough. So, when we calculate the Maxwell's equation or linear Maxwell's equation, what convention you are using, how you define your electric field. Since in this course we are defining electric field with a half term, we need to take account this half term, and that is why this term, this input term, which is a constant anyway, should change slightly and depending on the convention of your electric field. Well, with this note, let me now start our today's class. So, today we have lecture number 15, and today we have the elaborate expression of discussion on four-way mixing. So, what we have, let us try to find out. So, we have the cross phase frequency effect that we discussed in the last class, that under four-way mixing there are many possibilities that the frequencies can be generated. So, we find that in four-way mixing what happened, this omega 1, omega 2 and omega 3, if these three frequencies are there, which is launched together to a nonlinear medium where chi 3 is not equal to 0, then if combination of these three frequencies can generate another frequency, say omega 4. So, now omega 4 can be the combination of omega 1, omega 2, omega 3, and in general omega 4 can be represented by plus minus omega 1, plus minus omega 2, plus minus omega 3. So, these many terms one can generate, because for all electric field there is a complex conjugate term, and for this complex conjugate term we have a minus omega frequency associated with that, also minus omega 2, minus omega 3. So, their combination can generate many frequencies. This is one issue. Second thing is that it is not necessarily that omega 1, omega 2, omega 3 are distinct. So, there is a possibility that we have omega 1 is equal to omega 2. When omega 1 is omega 2, then there is slight change in this distribution, and we can see that there is a possibility that we have some frequencies with the combination of omega 1, omega 2, omega 3 with the degeneracy that omega 1 is equal to omega 2, then there may be some frequency that can generate which coincide with the original frequencies like shown here. So, omega 1 can be equal to omega 2 to 3, where how omega 2 to 3 is defined is shown here. These are the specific frequencies where this can be this combination of this frequency can coincide to the original launched frequencies. However, these launched frequencies omega 1, omega 2, omega 3 are separated with certain frequency difference, and if this separation is same as shown in here, it is delta omega, then this combination of omega I j k can give you different kind of frequencies, and among these different frequencies there are few frequencies that will coincide to the original frequencies. This is called the crosstalk. So, in fiber optics communication problem, so this crosstalk is a major issue. So, today we will going to learn more about this crosstalk, how this crosstalk can be eliminated, or if I want to generate a frequency which is with the same separation of the two frequency that is launched, then eventually we are generating a crosstalk frequency. So, how we generate the crosstalk frequencies, we will going to learn this course in this class rather. So, the problem is excitation of crosstalk frequency. So, we want to excite a frequency which is among these frequencies. So, there are 12 frequencies are there which we can say these are the some sort of crosstalk frequency with this definition that omega I j k should be equal to omega I plus omega j minus omega k. This is the structure of the frequency. So, I want to generate any of these frequency with this combination. So, if I do, so there is example that suppose I am generating omega 112. So, what is omega 112? Omega 112, we know that omega 112 according to our definition, it should be omega 1 plus omega 1 minus omega 2, because we know omega I j k is equal to omega I plus omega j plus omega k. This is minus omega k. This is the definition. This is the definition of the frequency. We are interested to find what kind of frequencies are there with these combinations. So, omega 112 is such a combination. So, that means if I launch omega 1 and omega 2 together as shown here, where omega 2 is greater than omega 1, then the combination omega 112 will give a frequency, we called it omega 4, and it will generate exactly in the same difference that we have between omega 1 and omega 2, but in the lower side. So, I launched the frequency omega 1 here, I launched the frequency omega 2 here, which has a separation delta omega, and due to the 4-way mixing process, omega 1 and omega 2 will combine with themselves, and they will generate another frequency, say omega 4, which is generated exactly delta omega apart from omega 1 as shown in this figure. Now, the question is if I want to generate omega 4, so how these things can be excited? So, what should be the differential equation of this field E 4, where E 4 corresponds to the frequency omega 4. So, omega 4 will generate as a combination of omega 1 and omega 2. So, that means omega 1 and omega 2 will be essentially the source term, the source field that will generate omega 4. So, I defined first E omega 1 and E omega 2, these are the input fields. So, omega 1 and omega 2 are the two frequencies. For these two frequencies, I have two fields, and these two fields are defined in this way. So, half E1 e to the power I k1 z minus omega 1, this is the field 1, and for field 2, which is which corresponds to the frequency omega 2, is I k2 z minus omega 2 plus complex conjugate. So, for these two field, if I now the next thing is to find out the source term, that means the nonlinear polarization term, that will basically leads to the source of different frequencies. So, it should be simply 1 divided by 8, because I know P nonlinear, several times we are using this expression. So, P nonlinear is epsilon 0 chi 3, then E total cube of that. So, we know E total cube means E omega 1 plus E omega 2 and cube of that, because E total means the total electric field that we have inside the system. So, here we have E1 and E2, this is the source term and cube of that in order to generate the omega 4. So, my P nonlinear is something this half, this half term, when I make a cube of that, we have 1 by 8, and it will be 1 by 8 epsilon 0 chi 3 and cube of the rest of the term associated with the electric fields. So, now P nonlinear is this. Once we have the P nonlinear, the next thing that we should note is the how many different frequencies we can generate with this combination. So, there are many frequency component you can generate, to be very honest. If I make a cube of these two, there in fact there are 4 terms. One is associated with frequency omega 1, another is associated with frequency. So, this term is associated with the frequency omega 1. This is associated with the frequency omega 1. This is associated with the frequency omega 2. And complex conjugate means we have another 2 frequency in our hand, which is omega 1 star and omega 2 star. Omega 1 star and omega 2 star means nothing that minus omega and minus omega 1 and minus omega 2. So, I have omega 1, omega 2, minus omega 1, minus omega 2 in this complex conjugate terms, and then cube of that. So, when you make a cube of that, we know there are different terms that will appear, but our concern here is only one frequency omega 4, which has the combination of omega 1 and omega 2 like this, because I want to generate only this frequency, and in order to generate this frequency, what should be my corresponding electric field, that is my concern right now. So, I just want to extract, there are many terms are there. So, A plus B plus C plus D whole cube. So, you can understand how many terms one can generate from this expression, but we should not bother about all the terms. We just want to find out which term contain omega 1 and minus omega 2, which combination of the electric field. So, this is easy to find, because omega 1 will be related to the field E1. So, omega 1 means 2 omega 1. So, 2 omega 1 will be related to the field E1 square, and minus of omega 2 will be related to a field which is E2 star, because this corresponds to 2 omega 1 and this corresponds to minus of omega 2. When I multiply these two things, that means the frequency will be added up, and eventually I will get the frequency component of this term is 2 omega 1 minus omega 2, which is nothing but omega 4. So, for omega 4 frequency, I will have only one term, and this is E1 square multiplied by E2 star. I just extract this term for the frequency omega 4, and if I write this here, then it should be U1, E1, E2. The term 1 by 8 epsilon 0 chi 3 will remain here as it is. Only thing is this cube, from this cube I will take only those terms which are having, which will have a frequency component omega 4 like this. So, that means this will be our term, but here you should very careful about this degeneracy factor 3, because in the previous class we mentioned about this degeneracy factor. So, how the degeneracy factor is determined in this case? So, we know that if 3 fields are distinct, for example, if it is E1, in this case there are 4 different fields E1, E12, E1, E2, E1 star and E2 star, there are 4 fields E1, E1 star, E2. So, there are 3 distinct fields. If 3 distinct fields are there, with this combination I will have a degeneracy factor 6. If they are same, any two of same, for example, if it is E1, E2, which is our case, then the degeneracy factor reduces to 3. And if all the fields are same, like one term we will have is E1 cube, the corresponding degeneracy factor should be 1. So, this way one can determine the degeneracy factor. So, here E1, E2, that means we have 2 distinct electric field. So, for 2 distinct electric field, by degeneracy factor will be 3 here. So, that is why the 3 term is sitting. So, that means now I have an expression of P nonlinear which containing a frequency omega 4. So, if I now write this P in as a plane wave kind of expression, then P nonlinear omega can be written as half P nonlinear tilde omega 4 and the corresponding frequency term. So, I write this entire stuff in this here with, so that means if I compare these two things, so P nonlinear tilde omega 4 is nothing but 1 by 4, then epsilon 0 chi 3 and then 3 multiplication of E1 square E2 star. These are the, this is the value of this so called amplitude. Also the exponential term will be there, we should not miss this exponential term. So, I 2 k 1 minus k 2 and z. So, all z dependent terms is here and the time dependent term I will extract like this, and we have a complex conjugate of that, because already the complex conjugate term is sitting here. Why I write this in this particular form? Because I want to extract this half, as I mentioned at the starting of this class, that this half is important, so that I can cancel this half for both the sides when you use the nonlinear Maxwell's equation. Well, after the knowledge of this P nonlinear at the frequency omega 4, the next thing is that to find out the corresponding electric field, the expression of the electric field or the differential equation of the electric field. So, in order to do that, we use basically the nonlinear Maxwell's equations or nonlinear wave equations, whatever. So, the equation is this, we are using this in several time. It should be E of omega 4 minus mu 0 epsilon of omega 4 d2 E omega 4 dt square is equal to mu 0 del 2 P nonlinear of omega 4 divided by dt square. So, this is our source term, and this equation we are using almost all the times when we calculate the evolution of the electric field amplitude. So, now E4 we know that when we extract these things or when we solve this part, so using the slowly varying approximation we always remove this term, that is one step we do. Also the next thing is that another equation, when we do that, one equation related to k square is coming, this k square E4. So, k square E4 is cancelled out by this term every time. So, when this k square E4 term there will be minus sign I guess, is cancel out to the next term, then eventually we have the first order derivative term in our hand, and which is 2 I k 4 d e 4 dz. This is the left hand side, and right hand side I have a derivative with respect to t of this term. Now, my p omega is represented in this way. So, when I make a derivative of the entire term with respect to t, this term will simply sit here, and e to the power of the frequency term will be there. So, this frequency term will cancel out from both the sides, because there is another frequency term to e to the power 4 e 4. So, the point is I can have a more compact expression here, which is equivalent to whatever the expression we have written here just before. That means, this is equivalent to the nonlinear Maxwell's equation. By applying the slowly varying envelope approximation and writing p in this particular form, in p tilde form. So, we have a very compact form. So, now what we will do? We will just write these things once again, and when I write these things, so I will write 2 I k here in the denominator, and the other things are the similar things. So, I will write d e 4 d z is equal to minus of so this minus will be replaced by I. So, this is already 3 by 4 term is there. So, I should have a 3 by 8 term because of this half, and then I will have mu 0 epsilon 0. Mu 0 epsilon 0 will be c square, which is here, and we have k 4 here, and in the numerator we have kappa 3 and omega 4 square, and then the rest of the term e 1 square, e 2 star, and exponential of this term is already there, 2 k I minus k 2 I z, and in the left hand side we have a k 4. So, k 4 will go here. So, I will have minus of I k 4 z. Now, if I write k 4 minus 2 k I plus k 2 is our delta k, then it should be minus of delta k, and rest of the term you can manipulate, because k 4 is omega 4 divided by c multiplied by n 1. So, 1 omega 4 c will cancel out. So, we will eventually have this equation. So, this is the evolution equation. This is the evolution equation of the cross phase, the cross frequency term, or the omega 4 term. So, crosstalk frequency, one crosstalk frequency or omega 4 one can generate, and this is the corresponding field equation or the field evolution equation. Now, the next thing is, if I want to excite these things, how to excite that? So, delta k is a phase matching. So, delta k has to be 0. That is the next step, because I want to excite these things. In order to excite, in order to increase the efficiency, what we need to do? We need to make delta k equal to 0. That means, we need to put absolute phase matching condition. So, if I do, then we will have exciting things. So, omega 4 is equal to omega 1 plus omega 1 minus omega 2. Here we have an additional information or additional thing, that is the difference between omega 2 minus omega 1, which is equal to delta of omega, is equal to the difference between omega 1 minus omega 4. So, this difference are same. That means, all the frequencies I can write in terms of omega 1 and delta omega. So, that means, here as it is written, so omega 1, omega 2 I can write as omega 1 plus delta omega, and omega 4 I can write omega 1 minus delta omega. So, in this way I can write the frequency omega 2 and omega 4 in terms of omega 1 and the related frequency difference, which is delta omega. So, delta k is our phase condition, the phase matching condition is delta k equal to 0. So, delta k is k 4 minus 2 k 1 minus k 2. So, delta k, k 4 is what? K 4 is the frequency propagation constant at frequency omega 4, k 1 is the propagation constant of the frequency at omega 1, and k 2 is a frequency propagation constant at frequency 2. So, once we have this term in our hand, then the next thing is we just try to find out delta k. So, I write delta k is equal to, change the omega 4 as omega 1 minus this term, k omega 2 I write k omega 1 plus delta omega here, and omega 4 I write k omega 1 minus delta 4 this, and k omega I write just omega. So, that means in terms of omega 1 I write my delta k. Once I write the delta k in terms of omega, next thing that we will do, we just expand is in Taylor series. So, if I do, then k of omega 1 delta omega can be expanded at k of omega 1 delta omega dk d omega at omega 1 and delta omega square divided by 2 d2k d omega square omega 1. So, we just expand this function as a Taylor series and we just take up to second order term, and then if I do that for this minus thing also, I will have a compact expression. You can see that k of omega 1 will cancel out with this k of omega 1 and 2 k of omega 1, which is a negative sign. Delta omega dk d omega is also cancelling out, and eventually we have delta k equal to delta omega square d2k d omega square at the frequency omega 1. Now, d2k d omega square is a quantity called dispersion, which is related to the refractive index deviation with lambda like this. So, d2k d omega square is called the dispersion term, how the k vector or the propagation constant is changing with respect to frequency. This is equivalent to how the refractive index is changing with respect to wavelength or frequency. So, there is a relationship between d2k d omega square is with the wavelength like this. So, I suggest the student to please try to do this calculation by yourself and check it whether you are getting this expression or not. So, the question, the thing is, if delta k equal to 0, that means d2k d omega square is equal to 0, that means d2n d lambda square is equal to 0. So, that means in order to generate the phase matching, absolute phase matching, in order to have the absolute phase matching, we have a frequency, we need to launch the omega 1 with a frequency such that d2n d lambda square is equal to 0. Now, this is a plot of n as a function of lambda in the left hand side, this is for KDP crystal. So, I can plot these things also with d2n d lambda square, the derivative of these things. When you plot the derivative of this quantity, you find there is some specific frequency where we have d2n d lambda 0. So, this is a frequency where d2n d lambda 0, below this frequency we have a positive value of d2n d lambda and negative value of d2 d lambda after this frequency. So, one case it is called the normal dispersion, in another case it is called anomalous dispersion, we will come to this later. But 0 dispersion wavelength is possible. If I launch the wave at 0 dispersion wavelength, what happened that we can excite, the phase matching condition will be valid at that point and we can excite our crosstalk frequencies, whatever the frequencies we are talking about here, which is omega 4. So, we can excite the frequency omega 4. So, with this note I would like to conclude here. So, today we learn how to generate any frequency, crosstalk frequency we take as an example, and what should be the corresponding field evolution equation, and if I solve this or if I partially solve this or if I want to find out what is the condition, phase matching condition, we find that if I launch the pulse exactly at 0 dispersion point, then there is a possibility that I will generate that frequency. But for fiber optics communication, this is harmful, because if you generate this crosstalk frequency, it will interact with the original pulse, and you will lose some sort of energy, or you will shoot some sort of the clarity of the signal will lost. So, normally we do not want to generate any kind of crosstalk frequency. In that case, the simple way that we just launch the input frequency far away from the 0 dispersion, so that the delta k become non-zero. If delta k become non-zero and high, what happened that we should not have any kind of phase matching, and the crosstalk frequency is not going to generate. So, with this note, let me conclude here. In the next class, we will go further and study more about the 4-way mixing. Mainly parametric amplification will be our main concern. So, thank you for your attention, and see you in the next class.